All right, here we go. We're making a video on pulley systems, a type of system that is common in introductory physics because it's great to learn how to apply Newton's second law. Not only that, we use pulleys in everyday life, as you can see in these videos over here. We use pulleys to transform forces to make our job a little easier to move things around. Your car, for example, if you look in the engine, has a ton of pulley systems. So how do we use them? How do we work with them? And how do we calculate things such as acceleration on pulleys is going to be the topic of what we're after. So we're first going to review what a simple machine is. Then we're going to learn how to calculate acceleration in pulley systems, particularly the Atwood's machine. And then we're going to do some complicated ones where we look at pulleys and friction. So what's a simple machine? If you remember from last year, a simple machine is any device that transforms forces to allow us to perform work easier. Okay, so half the battle of lifting something is, imagine if you had to lift something straight up all the time. That's difficult, and there's not enough room for that. So pulleys, or other types of simple machines, allow us to transform forces. I can lift something up by pulling in a different direction and a different vector. Okay, and the pulley allows me to transform that force, allow it to communicate to pull something up. Okay, so here's just a drawing of a hand pulling down to pull up. And in a gym, in these universal machines, they use pulleys to allow you to do that too. I can pull down in order to pull a weight up. What we won't talk about is multiple pulley systems that allow me to use less force to lift something up. We can talk about that later when we talk about engineering physics. But right now we're just focusing on single pulleys, rope around a single pulley. So all you need to know is that they transform forces. Okay, the Atwood's machine, okay, something that we looked at last year. The Atwood's machine is just a simple pulley with two weights, or two masses. Yeah, I'd correct myself there. Two masses attached on either side. One mass is heavier than the other. And what we've done is we've created a tug-of-war against these two masses such that one is going to win and the whole system is going to accelerate in a direction. So this system would accelerate in that direction. You would see the acceleration would go down. Okay, so how do we calculate acceleration in a pulley system? And the most important thing that you heard me say is system. That's important. We're talking about the movement of an entire system, not just one of the masses. Okay, so in order to do this, we have to apply Newton's second law. So Newton's second law states that if I have a net unbalanced force, it's going to cause an object to accelerate. Okay, so we need to find out what my net unbalanced force is. Then I need to find out what the mass of my system is in order to calculate my acceleration. So what is F net? Well, let's draw a diagram. Okay, so I'll keep this green. First of all, I have a force of gravity acting on that side. I have a smaller force of gravity acting on the other side because that mass is smaller. And the reaction is I'm going to create tension in the rope on one side is going to be a lot larger than tension on the rope on the other side. Okay, so I've created a tug-of-war. Okay, but this tension on this side of the rope is greater than that side. So that tug-of-war means that this side is going to win. So my net unbalanced force is going to be the force of gravity 2, I'm going to call this force of gravity 2, minus the force of gravity acting on object 1, that's my net force, is going to be equal to the mass of the system. Now, even though this is winning, the whole object, everything is going to be moving together. So the mass of the system is going to be the mass of everything, m2 plus m1. And technically, I would have to also add the mass of the rope, but let's imagine I'm using a rope that has like almost no mass, so I don't have to worry about it. We'll call it massless. And that'll give me the relationship here. Now I just have to isolate for my acceleration. And I've created the relationship that would allow me to calculate for the acceleration of that system. So as long as I can calculate the force of gravity, the mass m2 times g, okay, so let's just fix that, m2 times g, okay, over m1 times g. Now I could even factor out the g and I could put it over here and then have g times m2 minus m1, and then I've created an even bigger relationship. But that's simple, okay? That's as simple as we get. And might as well just do it for to show you guys how I could create a relationship that looks like that. Okay, and then I've created a formula that I can plug into a spreadsheet and be able to calculate the acceleration of any mass system. If I knew M2 and I knew M1 on a pulley system, I'd be able to calculate the acceleration of any pulley system if I plug that into a spreadsheet. So that's the relationship that we just derived for acceleration on a pulley system. Okay, so let's do a sample calculation of a pulley system. Let's imagine I have 10 kilograms on this side and 5 kilograms on that side. Now I'd go back and I was solving this problem, I would draw my free body diagram to illustrate all this. But since I've just done that over here, I'm just going to skip all that and use the equation that we've created. All right, so the equation was G m2 minus m1 over m2 plus m1 is equal to my acceleration. So then 9.81 meters per second squared times m2 minus m1 divided by m2 plus m1, which is going to be 10 kilograms plus 5 kilograms, will give me my acceleration. Okay, so then in the end it would be 9.81 times 5 over 15 is equal to my acceleration. So one thing I can look at here is I would say that my acceleration is going to be one third of the acceleration of gravity, thanks to this counterweight, this counterbalance. So I can say, I'm not even using my calculator for this one, but I'm going to say it's roughly around let's say 3.1. I'm sure it's a little bit more than 3.1, but I'm not using my calculator. So I just made an estimate and said that this is one third of that. Maybe it's 3.2. Yeah, probably 3.2. Okay, great. Next, let's look at pulleys and friction. So this pulley system is using just gravity. Okay, the counterweight here is slowing the acceleration of the system. The bigger the counterweight, the slower that system is going to accelerate, as you can see from here. But now we have a pulley on a tabletop, and we've also explored this before. And it's a great system to use to explore friction coefficients. So if you're an SL student and you want to design an IA where you're looking how does a change affect a friction coefficient, this would be a good system to use. Okay, and you're armed with that. You have this after this video to be able to design that if you want to. So how does this work? How do we factor in friction? This mu is my friction coefficient. So how do we factor it in? Let's just review and draw a free body diagram. So that's my force of gravity, and that's my force of tension. Okay, this is the force of gravity. That is my normal force. That is going to be my applied force, the force of tension. Okay, that's my force of tension here, that's applying. Okay, because gravity is working in a different direction. It's not even factoring in. And then that's going to be my frictional force. Okay, so in order for this system to move, gravity is pulling down, which creates tension that's being transformed to pull in that direction. So what's opposing the pulling in that direction? The force of friction. Gravity has nothing to do with this. The force of friction is the only one working against the pull. Okay, and the ultimate acceleration is going to be in that direction. So how would I apply F net is equal to ma? Well, let's solve for F net. F net is going to be equal to the force of gravity on object M. Okay, this one here, the force of gravity, minus the force of friction, because that's the only force opposing the pulling, okay, is going to be equal to m plus m. Okay, the two masses, we're assuming the rope doesn't have any mass, so little m plus m times acceleration. Now let's get down a little further. mg, little mg, minus, now for the force of friction is equal to the friction coefficient times capital M times g is equal to m plus m. Okay, so now let's isolate for the acceleration. Okay, and then if I went a little further, I can factor out these g's. So then how do I do that? I'm left with g m minus mu m over m plus m is equal to my acceleration. So now I've created a relationship that I can plug into a spreadsheet, and calculate whatever I want with a pulley system on a tabletop. I just need to know the friction coefficient. I need to know the mass. I need to know that mass, and I need to know the acceleration of gravity, and I'll be able to find the acceleration on that pulley system. Now, here's one more layer of complication. I have two things. I got a pulley on a table, and I got an Atwood's machine. Okay, so how is this going to work? Let's take a look. So F net is equal to ma. Let's just draw these in. That's the force of gravity. This is a smaller force of gravity. That's a smaller force of tension. That's a much larger force of tension, which is going to be pulling on that side. And that smaller force of tension is going to be pulling on that side. Then there's also going to be friction, and friction is going to be with whatever direction that pulley is. It's going against that direction. Now I can say this object here is a lot heavier than that object, so tug of war is going to favor that and go into that direction towards the right. So then I would have an additional frictional force over here, okay? And let's say that mu is equal to 0.1, okay? A very small amount of friction. Okay, so how would I calculate that? Well, F net is going to be Fg of the 3 kilogram object minus Fg of the 1 kilogram object minus the force of friction is going to give me the total mass times the acceleration. All right, and so how are we going to do this? So 3 kilograms times 9.81 meters per second squared minus 1 kilogram times 9.81 meters per second squared. Now, how would I calculate the force of friction? It's going to be equal to 0.1, which is the friction coefficient, times 2 kilograms times 9.81. Okay, you see all this? Now, that was a big mistake that I started plugging numbers in rather than do what I did over here, which is to create a relationship. I could have easily created a relationship, rearranged it, and then plug numbers in. Now I'm running out of space, okay? I don't like what I just did. All right, so what I have to do here is I have to move this over here so I have more space. Okay, and what I've created here is my net force, that's F net. Okay, is going to be equal to the total mass of the system, which is going to be 3 kilograms plus 2 kilograms plus 2 kilograms plus 1 kilogram, okay, times acceleration. So 3 plus 2 plus 1 is 6. Okay, so if I divide by 6 kilograms, that cancels out. Divide this by 6 kilograms. Okay, and then if I plugged all of that into my formula, I should be A-okay. All right, so let's go do that right now. Okay, now what I'm going to do, just to make this simpler so I don't have to do a lot of multiplying of the same thing, is I'm going to factor that out. So 9.81 meters per second squared times 3 kilograms minus 1 kilogram minus 0.1 times 2 okay, and then all of that over 6 kilograms is going to give me my acceleration. So let's go do that. Three minus 1 minus 0.2 times 9.81 divided by 6. That gives me an acceleration of 2.94 meters per second squared is equal to my acceleration. All right, and that's that.